Hello students, I am Dr. S.B. Tuljapure, Associate Professor, Department of Mechanical Engineering, Walchand Institute of Technology, Solapur. So in today's session, we are going to deal with the velocity triangles in centrifugal pumps. The learning outcome. At the end of this session, students will be able to draw velocity triangles for centrifugal pumps. That is, you will be able to draw the inlet velocity triangles and outlet velocity triangles for the centrifugal pumps. So that is going to be the learning outcome of this particular session. Now let us first see what are these velocity triangles. Velocity triangles are the vectorial representations of different velocities of liquids and veins. Okay. So see that we are going to have the velocities of the two different things. One, it is liquid, and the second one, it is the solid part, that is the vein or the blade we are having. And in case of these, there are going to be the different velocities. The different velocities are like absolute velocity, then the relative velocity, then we are going to have the velocity of flow, then the whirl velocity we are having, then velocity of vein will be there at inlet and outlet, etc. So all these velocities, absolute, relative, etc. So all are going to be at inlet and outlets. So we are going to deal with the triangles which are going to represent these all velocities, how they are, at what angles they are, in what direction they are. So like that we are going for. So the velocity triangles we are going to draw in case of the centrifugal pumps. So now, before going to the velocity triangles for the centrifugal pumps, let us first have the nomenclature of the different parameters. So letter U we are going to make use for the velocity of the impeller, or the blade it is, okay, or the vane we can call it as. So then V, it is going to be used for absolute velocity of the liquid. Okay. V suffix W it is. Okay. We are going to make use of this one for the whirl velocity of the liquid. So it is the tangential component of the velocity, absolute velocity. Then Vf, so it is the velocity of flow of liquid. So it is the radial component of the absolute velocity. So whirl component, it is tangential component of the absolute velocity, and velocity Vf, that is the velocity of flow, it is the radial component of the absolute velocity. Vr, it is the relative velocity, as earlier said. So we are having the velocities of the solid components like blades or veins and the velocity of the liquid. So the relative velocity, it refers to the vectorial difference between these two. Okay. Then we are going to make use of the suffix 1 and suffix 2 for the entry and exit, or you can call it as inlet and outlet. And as in case of the centrifugal pumps, we are knowing that it is we are going to have, with the reference to this one, entry, it is going to be at the eye of the impeller. So radially outward flow it is going to occur. So in case of the suffix 1, inner diameter, say it will be used. So for suffix 2, outer diameter of the impeller will be there. So the other parameters, these are alpha and theta. These are the angle made by absolute and relative velocities with the direction of the motion of the vanes or the blades. Then we are having beta and phi, the corresponding values, but at the outlet. Okay. Now think of the importance of the velocity triangles in centrifugal pumps. Why we are interested to go for, or we are going for velocity triangles in case of the centrifugal pumps. Okay. So see what velocity triangles, in what way velocity triangles will help us. Okay. Velocity triangles allow engineers to analyze and optimize the pump's performance by calculating key parameters like head developed, power required, and blade angles needed to achieve the desired flow rate and output pressure. Means you can say that we can go for the changes in the design, or initially when we are going to design the centrifugal pumps, at that time the various parameters can be say determined by drawing the velocity triangles. So we want to optimize the pump's performance, and our requirements are like output pressure should be certain, we should have a certain value, then the flow rate should have a certain value, like this. When we are interested to achieve all these, we need to consider these velocity triangles. Okay. Before going for the velocity triangles of the centrifugal pump, let us first see how the velocity triangles are for a generalized rotodynamic machine it is. Okay. So we are going to have these as blades or the vanes. Okay. So this one it is the inlet side, and this one it is the outlet side. Okay. So this one it is considered to be radial inward type of the flow, whereas in case of this centrifugal pumps we are having radial outward. Okay, so that we should remember. Then now first of all, the jet which is coming, so it comes out in this particular direction, and with a velocity it is v1. So see that v1, it is the velocity of the jet or the liquid which is coming at inlet side, and this v1 is called as absolute velocity. Okay. Now we can have the two components of this absolute velocity. One component it is the whirl component, which is the tangential component, and the second component it is the radial component, which is the flow component. Say that this vf1 it goes to the center, okay, or the meets at center. So vf referring to the velocity of flow, vw referring to the say tangential direction, so it is whirl component. So at inlet we are having this absolute velocity as v1, so whirl component as vw1, and the flow component as vf1. So the angle it will be alpha, so between the tangential direction it is, so in this direction we are having, so angle between this v1 and the blade velocity. So these blades are mounted on a rotor and we are having the anti-clockwise direction, so tangential velocity it will be towards right like this, and we are having this angle at alpha. Okay, so we are having the velocity of the vane corresponding to suppose pi dn upon 60 like that. If you make use, so you will get the value of u. So at inlet section it will be u1. So it is, now we are having the vectorial difference v1 and u1, so vr1. Okay, so vr1 it is the relative velocity, and the angle made by relative velocity with the tangential velocity of the blades, it is the theta. So referring to the outlet side, we are the jet it is leaving with a velocity vr2. Okay, we are having the say tangential velocity of the blades or the vanes u2. So then this one comes out to be v2. So then the flow component it is vf2 and vw2. So these angles beta and it is phi. So we will refer this diagram and we will modify this one so that we will get the velocity triangles for the centrifugal pumps. Okay. See now this diagram it is shown here. So inlet side we are having here, and this one it is the outlet side. So now centrifugal pumps we are the radial outward flow type. Okay. So in case of this one, a radial velocity it is like this, or radial component. Okay. See that here it was v1 was inclined, because of that one we were having whirl component and the flow component like this. But this v1, when it is going to be on the radial line itself, so this v1 will be nothing but it will be equal to vf1, and value of vw1 will be equal to 0, and this v1 it is going to make 90-degree angle at that time with the tangential component. Okay, so see that v1 it is radial outward, v1 is nothing but is equal to vf1. Okay, so it is going to make 90-degree angle with the tangential velocity. This alpha is nothing but it is a 90-degree, and then we are having the tangential velocity of the blades at the inlet. So the blade it is moving in the anti-clockwise direction, So this one u1 in this direction. So it is v1 and u1 we are having. The relative velocity it is vr1, and the angle made by vr1 is equal to, it is theta. Okay. Now at the outlet side, that is at the outer outlet side, that is the impeller diameter, it is going to be outer. So the liquid, it is leaving with a relative velocity, it is vr2. Okay. Then as the radius 2, that is the outer diameter, at the outer side the liquid is leaving, so pi d2n upon 60 if we are going for. So in case of that one, the value of u2 comes out to be larger than u1. Okay. So in case of this one, from this particular point, draw the line representing u2. So this is u2 and this is vr2. So this one, it is going to be v2. The two components of the v2 we are having as flow component radial, okay, and whirl component tangential, it is vw2. Angle made by this v2, that is the absolute velocity, it is going to be beta, and angle made by this relative velocity with the tangential component will be phi. So like that, what we should do is, we should go for firstly the generalized diagram or the velocity triangles for the rotodynamic machines. Then with reference to the type of the rotodynamic machine, whether it is a turbine or a centrifugal pump, etc., that is power producing or power consuming devices. So what is happening, how the flow is, whether radial inward, radial outward, etc., so how the things are occurring. So accordingly these triangles can be modified, and making use of these triangles initially for understanding purpose, and how these triangles are getting modified here, so that can lead to the better understanding. So these are the velocity triangles for the centrifugal pumps. So the points to be noted, v1 is equal to, it is absolute velocity is equal to velocity of flow at section 1. Value of whirl velocity at section 1, it is equal to 0, or at inlet it is 0. Alpha is equal to 90 degree. At outlet, u2 is going to be larger than vw2 at outlet of the impeller. These are the references used for this particular session. Thank you.